Welcome back. Today, we're going on a tour to check out a hidden mathematical tool that, it pretty much powers our entire digital world. It's called the Wavelet. So let's figure out what it is and why it's such a game changer.
This quote really hits the nail on the head. Think about it. Our brains are totally wired to notice change. It's not the constant, steady drone that gets our attention. It's the sudden shifts, right? The abrupt stops. And these are what engineers and mathematicians call transients. So, that leads us to the real challenge here. How can we build a tool, a mathematical one, that can actually see these sudden changes? That's really the quest we're on in this explainer. We're looking for a tool that's sharp enough to analyze these super fleeting but incredibly important moments in any kind of signal. Okay, first things first, we've got to understand this world of transients. We're talking about sudden events, anything from a clap of thunder to a sharp edge in a medical image. These things are not only packed with information, but they are also just incredibly difficult to analyze with the old school methods. You see, for the longest time, signal processing was all about stationary signals, things that are steady, predictable, kind of like the hum of your refrigerator. But all the interesting stuff, it's usually in the surprises, these non-stationary, transient events. The key thing to get here is that our world is just full of these changes, and we need a tool that's built specifically to see them. So, let's make our first big stop on this tour. We are stepping into what's been called the powerful Fourier kingdom. And here, we're gonna meet the long-reigning king of signal analysis, the Fourier transform. The Fourier transform is basically a mathematical prism. Seriously. Just like a prism can take white light and split it into a rainbow, the Fourier transform takes a really complex signal and breaks it down into all the individual frequencies that make it up. Imagine an orchestra playing. The Fourier transform can tell you every single note being played. Its power to see the what is just undeniable. Okay, but this slide really gets to the heart of the problem. For a stationary signal, like that continuous hum, all the frequencies are there all the time. And for that, the Fourier transform is absolutely brilliant. But what about a transient signal, like a really sharp clap? All those frequencies, they appear and disappear in a split second. So what happens when the Fourier transform tries to analyze that? Well, here it is. This is the Fourier transform's fatal flaw, at least for analyzing our transient world. It completely loses all track of time. It can give you a perfect list of all the frequencies, the what, but it has absolutely no idea when they happened. It's like someone hands you a musical score, but it's just a list of all the notes in the symphony. There's no rhythm, no timeline, nothing. You know the notes, but you have no clue what the music actually sounds like. So clearly we need both, right? We have to unite time and frequency. Let's take a look at the first real attempt to pull this off. The so-called time-frequency wedding, a way to finally get the what and the when all in one analysis. This is the ultimate goal. How do we build a tool that can analyze both what frequencies are in a signal and precisely when they show up? To go back to our music analogy, we don't just want a shopping list of notes. We want to know exactly when each note was played, how long it lasted, and in what order. We want the whole shebang. So the first big attempt to solve this was something called the windowed Fourier transform. And it's a pretty clever idea. Instead of looking at the whole signal all at once, you slide this listening window of a fixed size along the signal. You do a Fourier transform on just that little piece inside the window, then you slide it over, and you do it again and again. This actually gives you some idea of when different frequencies are popping up. But, and this is a big but, there's a huge catch. That listening window has a fixed size, and that is its fundamental weakness. It's kind of like trying to explore a huge, beautiful landscape, but the only tool you have is a pair of binoculars that are permanently stuck at one magnification. You can't zoom in to see the details on a butterfly's wing, and you can't zoom out to see the whole mountain range. You're just stuck with one perspective.
And that brings us to the final destination on our tour, which, you'll see, is a truly elegant solution to this problem. We're about to meet the Wavelet, and it acts like a mathematical zoom lens. So what in the world is a wavelet? Well, the name itself is a pretty big clue. It's literally a small wave. Unlike those infinite, never-ending sine waves of the Fourier transform, a wavelet is a short, localized little pulse of energy. And its superpower? Its ability to be stretched or compressed, to completely change its scale on demand. So here's how that zoom lens actually works. It's what's called a multi-resolution analysis. First, you scan the signal with a wide, stretched out wavelet. This is your zoomed out view, right? It's perfect for finding the big, broad, low frequency stuff. Then you shrink the wavelet way down, compressing it to a much smaller scale. And finally, you rescan the signal with this teeny tiny wavelet. This is your zoomed in view, and it lets you pinpoint the exact location of those sharp, high frequency transients. It's a process that can see the whole forest and then zoom right in to inspect the veins on a single leaf.
And this comparison just sums it all up perfectly. Where the windowed Fourier transform gave us that fixed listening window, the wavelet transform gives us an adaptive zoom lens. It's not a one-size-fits-all solution. It literally changes its scale to match whatever feature it's looking for. And this is what makes it so incredibly good at analyzing the transient signals that other methods just can't handle. It finally gives us what we've been looking for, a crystal clear view of both the frequency and the time at any level of detail we could possibly need.
Okay, so we've covered a lot of theory. Let's bring this whole tour home and talk about why this mathematical zoom lens actually matters. I mean, where does this powerful tool show up in our day-to-day lives? Well, the short answer is pretty much everywhere. Wavelets are the hidden engine behind so much of our modern world. You know that JPEG 2000 image format? That's built on wavelets. The ability for doctors to see those super fine details and sharp edges in an MRI scan? Yep, aided by wavelets. Noise reduction, pattern recognition, they all rely on the unique power of wavelet analysis.
When you boil it all down, wavelets give us a much sharper lens to see our complex, transient world. By being so good at capturing the abrupt changes and tiny details that traditional Fourier analysis just flat out misses, they let us store and send complex information, like images, way more efficiently and with much better quality.
And you know, this whole tour leaves us with a really fascinating final thought. The journey from Fourier to wavelets, it shows that sometimes the biggest breakthroughs don't come from finding new data, but from inventing a whole new lens to look at the data we already have. It really makes you wonder, doesn't it? What else are we missing right now, just because we don't have the right lens to see it yet?